Welcome back. In the previous context, we have talked about features as corner points or edges. But what if I tell you everything you see around you is a feature? In today's episode, we will see blobs as features. We will demystify how features can be rethought with arbitrary shapes. So let's dive right in. If you remember, NASA's Ingenuity helicopter was the first aerial robot or uncrewed aerial robot which was deployed on a foreign planet, in this case Mars. I'm going to play a video of the Ingenuity helicopter basically taking a completely autonomous mission on its own with just onboard sensing and compute. As you see here, it takes off, basically like does a lap, and then it will eventually come back. This was great because we could do a lot of missions, so on, and this is how the onboard camera on the bottom looks like, which is used for knowing its position relatively with respect to the starting point, so it can actually fly autonomously and come back. On flight 72 on Jan 18th, 2024, it sustained rotor damage, which was permanent and left it unflyable. So if you look at the shadow here, the damage is basically pretty intense to the propellers, where the half of the propeller is like broken out or shredded itself, and it could not fly anymore. One of the main reasons why this happened was Ingenuity used a down-facing VGA camera running at about 30 Hz for monocular feature tracking. So which basically uses these features to know the apparent motion between the frames. Remember, in the previous cases, we have talked about how matching features is super important and it needs to be robust. The problem was basically it went through a patch which was basically featureless and essentially just failed. And because it couldn't estimate how it is, and it wrongly estimated the angle and like crashed pretty badly. So the whole point of the episode today is to talk about how we can actually have robust feature matching in scenarios like these, which are actually really hard to come by, so that like things like this does not happen. So let's quickly recap from the previous episodes what we have been seeing. We have the image of Lena. We said we'll forgo the color because grayscale is enough for features, and then we will take a simple row. To see what is important in this row, let's zoom in and let's plot the intensity versus location. And we already talked about the fact that these like kind of intensity plots are super important because we want to detect edges in these intensity values, right? Let's take a simpler example where we have a rising edge and a falling edge. What we can do is we can basically take the gradient operator or this first order gradient like the Sobel operator. And if you have not seen this, I would urge you to see the episode on edge detection where we actually cover this in extreme detail, right? With the gradient operator, we obtain the local extrema that indicate edges. In this particular case, we basically threshold for an upper spike or a lower spike, which works out pretty well, but it's actually very noisy. Instead, what we can do is we can take the second order gradient. With the second order gradient, we just have to look for zero crossings. And it becomes a much simpler problem to model in optimization. And so that's what we are going to use in today's video. So the Laplacian operator, denoted by nabla square in this case, is denoted as follows. Imagine you're applying the gradient operation like the Sobel operation twice, and that gives rise to the Laplacian operator. And here epsilon is the patch width or height, so it's applied in a small neighborhood. So when we combine these two things, nabla square IE is given as the sum of these two second order gradients. The question is there directionality here? Which means that in like the Sobel operator, we could take the tan inverse of y to x and we could actually get the orientation of the edge. Can we do something like that in the Laplacian? The answer is a no. And so why? Why can't we do that? In this particular case, since we are adding both the values, the operator is rotationally symmetric. So we cannot actually do that. And if you're wondering how does this operator look like, for a simple Sobel kernel, which we have seen before, So like this is what the Laplacian operator is going to look like on the first one. In the second one, this is a smoother Laplacian operator, and it varies like a Gaussian so that it's a little smoother. Let's see how the Laplacian edge detector works on our Lena image. So if you apply the Laplacian edge operator, this is what it looks like, and you actually threshold it to find 0 crossings. This is what you would see. It's pretty good. And if you remember from the canny edge detection lecture, it's almost similar to that without actually doing any fancy processing. So this is pretty cool. So, but in reality, the issue is it's never going to be this smooth. The rows of the image are never going to be this perfect. So there is always going to be noise added on top of that. Right? To make life simple, let's only look at like the one half of that edge to make life simple. If you simply take the gradient operation, it's actually very noisy. Here the edge technically is there. It's one of the spikes, but it's really hard for us to know the difference between the edge spike and the other spikes, which are basically due to noise. So instead what we will do, as we have done in the past, is we take a smoothing kernel like a Gaussian kernel to get rid of noise. And so we apply the Gaussian kernel, it smooths out our input waveform, and then we apply the gradient operation on top of that. Okay? And we will get a spike on this, and remember that the spike is not going to be a direct delta spike, it's going to resemble more like a Gaussian in this particular case. So what we can also do is to apply this for the Laplacian. We can take the gradient of the Gaussian itself, and so when we apply this, we basically get the second order derivative or the Laplacian of Gaussian operator, which looks like the green one there. So if we plot the Laplacian of Gaussian operator, this is what it looks like, and this beautiful concept was coined by David Marr, who is one of the pioneers in the field, and we've seen Marr in the Marr's theory of computer vision before, and you have the David Marr Prize as the best paper ICCV. So now let's just quickly recap. Let's look at the gradient of Gaussian, which is like the smooth Sobel, and the Laplacian of Gaussian, which is like the smooth second order derivative. So a Gaussian kernel looks like this in 2D, and if you take the x gradient of the Gaussian, it looks like that. The y gradient of the Gaussian is the opposite of that, and the Laplacian of Gaussian looks like this. The Laplacian of Gaussian operator is also called the inverted sombrero or the Mexican hat operator because it looks like the sombrero Mexican hat as you see in the image here. So let's quickly compare the mathematical properties of these. So in the first order gradient, we have basically the location, magnitude, and direction of the edge. In the Laplacian, we only get the location of the edge because it's radially symmetric. On the left hand side, it's detection using a maxima. On the right hand side, it's detection using a zero crossing, which generally turns out to be better. On the left hand side, it's a nonlinear operation with two convolution operations. And on the right hand side, it's a linear operation with one convolution operation. So now the question is, what happens if we take one Gaussian and we take a different Gaussian with a different sigma and actually subtract them? How does that look like? I would want you to pause the video for a second and quickly take a pencil or a paper and just draw it out with your hand and see how this would look like. And if you drew something like this, you would be absolutely correct. And you might be thinking, hey, this looks very similar to the sombrero hat operator we saw before, right? Or the inverted sombrero hat operator like before. You would be absolutely correct. This is the approximation to the Laplacian of Gaussian, and it's called the difference of Gaussian or the dog operator. So now let's take a side step and let's look at features in a new light. Remember that in the previous cases, we were detecting features with square neighborhoods. But the question is, why does it have to be square? Let's look at that in a second. So now let's look at this image, which has three different radii of circles. And each of the radii are doubling as you go from left to right. And let's just take one slice of this image. And I'm going to just color code it. Remember that color is not being used for processing here. This is just for a representation so we can follow along where each of these blobs are going. Okay. So if you plot this, this looks like a Gaussian distribution almost. And if we take a Gaussian kernel of certain size, and then we take the Laplacian or the difference of Gaussian operator, and then we apply it on the original image by convolving them. This is what we would see. So let me move these plots upwards to make a little bit more space. And because the scale of these are pretty different, like basically the red curve is much taller in peak than the green one, and that is much taller in peak than the blue one. Let's normalize this. So let's normalize this by multiplying it with the sigma square, which is the standard deviation of the Gaussian, which we started with. So if you do that, you will see that there is a nice beautiful peak on the red one, and the peak starts getting split into two peaks as you go to the green one and then the blue one. Now let's do the same exercise again. Let's bump up the value of sigma. In this particular case, let's double it, and let's do the same process one more time. You will see that there is a small peak in the red one, there is a small peak in the blue one, but the green peak is much sharper and much taller, right? Which is great. Let's do that one more time. Let's bump up the sigma twice. And if you look at this again, you will see that there are peaks in the red and green ones, but the blue one actually has the largest peak. Now let's look at it from an image perspective rather than a single row. This is what we had, and we have sigma 1 as 25 pixels in this particular case, and we have sigma 2 as basically square root of sigma 1, and we are implementing the Laplacian as a difference of Gaussian, where sigma 2 is computed as root 2 times sigma 1, right? And we implement that and we do the normalization. This is what it will look like. We clearly see a spike in the first one like we saw in the 1D example. Beautiful. Let's do this one more time. So we have start with sigma 1 of 50, and this is the sigma 2 value. And if you start carefully observing, the leftmost small blob almost disappears, and as we start blurring more and more, and clearly the spike is in the second one in this case. Beautiful. Let's do this one last time. So we start with a sigma 1 of 100, wherein the first one is almost gone, the second one is almost gone, the third one is quite prevalent, and we do the sigma 2 as square root 2 of sigma 1, and then we do the same operation as you've been seeing before. Clearly, we can see that the third blob is beautiful. After this video, you might be wondering what just happened here, right? Let's quickly recap. So different blobs peak at different scales. Scale here refers to what my sigma of the Gaussian was, right? So let me show you what that meant. So the red one peaked at a smaller Gaussian, the green one at a slightly bigger Gaussian, twice in this case, and the blue one at double that of the green one, right? So let's call it sigma 1, sigma 2, sigma 3. Scale at which we get the maximum response for the normalized value of Laplacian is called the characteristic scale sigma star. In this particular case, sigma 3 is greater than sigma 2 is greater than sigma 1. Remember that the characteristic scale is proportional to the blob size. Of course, because we know that the characteristic scale is proportional to the blob. Remember that the characteristic scale is proportional to the blob size. Particularly in this case, we had sigma 3 double of sigma 2, which is basically double of sigma 1, or sigma 3 is 4 times that of sigma 1. So if you want to actually implement this in code, you would actually write some optimization function, and that's what you will write in your paper, right? Let's quickly go through that. Given an image I, we want to compute this quantity, sigma square, nabla square, g sigma convolved with I at many scales of sigma 1 to sigma n. This will be called the scale space. And this quantity, sigma square, nabla square, g of sigma, is called the normalized Laplacian of Gaussian, or n log. And the optimization problem is essentially to find the blob position and the characteristic scale or blob size where we actually peak the n log, or the absolute value of n log. So just to quickly recap, this is what g sigma looks like, this is what the Laplacian of Gaussian looks like, or the difference of Gaussian looks like, and this is what the scaled Laplacian of Gaussian looks like. Remember that the location of the blob is given by the local extrema after applying n log on multiple scales. Okay, the concept of scale space is very cool. Let's look at it from a completely different perspective. So you have this image, and scale space essentially refers to us operating at different resolutions, or in other words, it's basically different amounts of blur, right? Or what we would see with basically that lower resolution scaled back to the full resolution, right? Increasing sigma basically refers to a higher scale, which means it decreases resolution, which means that it's increasing blur. Let's take the exact same point. In this case, it's the edge of the bar in this case, and let's plot the n log value with respect to the scale value. You can clearly see that the values of sigma are changing, and in the second case we see that this is basically where we found the extremum value. So which means that this double of this sigma 1 will basically be the radius of the feature, which will actually give you the most robust estimate of the feature descriptor. So this is from a stark departure to what we have been seeing before, wherein we had like square shaped or rectangular shaped feature neighborhoods. In this case, we have circular shaped neighborhoods, which is very cool. And remember that this is circular because we started with a Gaussian distribution, but you can start with any random distribution and it will basically be the unit of or unit ball of that distribution itself. Beautiful. So now let's take a different point in the sky and let's do the same exercise again. You will see that there is no strong extremum, which means that this is not a blob. If you don't remember the lecture where we talked about Harris corners, I would urge you to go back and look at that one more time, where we talked about if you don't have gradient changes in both directions, it's not really a good feature vector, right? And that's exactly what you're seeing here, where you do the n log versus different scales. If there is no maximum in this, it's actually not a good feature. And that's what we are seeing with the sky here. But we saw a good feature in the corner of the barn there. You might be wondering, okay, this seems pretty ad hoc. We started with circularly shaped things, but is this even important, right? So the answer is this is actually super important, and nature uses this almost all the time. So the bee, the honeybee, utilizes the polarization of light to basically navigate itself like a visual compass. So it understands where the north is, where the south is with respect to relation to the sun, and it utilizes that to fly. And that's why if you see like honeybees, they generally don't fly in the dark or where the sun is down, or if it's like really cloudy, right? This is one of the reasons for that. So let's look at like these flowers are beautiful, right? They're nice and yellow, but colors of the flowers come in various shapes and forms, and it might actually be really hard for a small honeybee brain to be able to detect all this stuff. How does the honeybee do that? Remember, I told you a little trick that it uses the polarization of light. From the view of the honeybee, these flowers actually look like this. Remember that they don't really see the color yellow. This is just a visual representation, but they see the dark spot in the middle of the flower, wherein it is basically looking for these bright visual cues, and they look like landing zones, right? And this is what it looks like. And obviously the resolution the bee sees at is like what is shown in D. Clearly, just detecting blobs at different scales tells the honeybee which flower it should land on, right? So the honeybee essentially does something very similar to what we have been seeing in terms of detecting blobs at the neuronal level, and it works out wonderfully well. So just to quickly recap and check the understanding, what mathematical operation do you use to detect edges? Why is the Laplacian better than the Sobel operator? What are blobs in the context of features? How can blob be a feature? And how did we actually use them? See you next time. Take care. Bye-bye.